In this video, we will learn about reduction, which is a very important theoretical result, and it is essential to understand other theoretical results such as NP-complete classes, NP-hard classes, and decidability. Assume that we are given a Turing machine N and N decides language B. That means if the input W is in language B, then N outputs yes, otherwise it outputs no, but it holds in either case. We are not allowed to modify Turing machine N or look inside it. That means that Turing machine N is treated as a black box. Now we can create a new Turing machine M which decides a different language A by transforming the inputs of language A into the inputs of language B via a polynomial time function f. So f provides us a mapping, a polynomial time mapping from the inputs of language A to the language B. If such a function exists, then we can say that A is polynomial time reducible to B. Formally, we can define the polynomial time reduction as follows. A language A is polynomial time reducible to language B, written as A polynomial time reducible to B if a polynomial time computable function f that maps strings to strings exists such that for every input string W is member of A if and only if f of W is member of B. That means every input string of A can be mapped polynomial time to the input string of language B. Please note that reduction is transitive. It implies that if A is reducible to B and B is reducible to C and C is reducible to D, then A will be reducible to D and B is reducible to D, or A is reducible to C. This transitive property will be useful when we will be talking about NP-complete problem in a future video. Now let's understand reduction with a simple example. We will do more complicated examples later on, but let's start with a very simple example. In this example, we are given a Turing machine N, where N can answer that if a shortest path in a DAG exists with a specific cost. So N basically finds us a shortest path in a directed acyclic graph. So this problem will work only in the directed acyclic graph, will not work for the general graphs. Now we can transform this shortest path problem to the longest path problem by changing the input of our algorithm. At the input, if we change the signs of our the signs of the weights of the graph, then the same machine that was finding shortest path previously will gives us the longest path. And negating the sign of the graph requires only polynomial time. That means big O of cardinality of edges, because we have to loop through all the edges and change their sign. So this very simple transformation is termed as a polynomial time reduction of a language A into a language B. In this case, language A is the longest path and language B is the shortest path in the tag. So we will do more examples of reductions, which will be more complicated and more comprehensive. But that is it for this video. If you like this video, please don't forget to buy me a cup of coffee or support me in any way. Thank you for your support. See you in the next video. Bye.